This is a practice quiz which I'm going to work out in two separate videos. In this first video, we will explore the graphical relationship between the original function f and its first derivative f prime and its second derivative f double prime. Number 1, state an x-coordinate at which f of x is continuous but not differentiable. They are talking about a cusp or a sharp turn. And I see that we've got a sharp turn right here. So f is continuous but not differentiable at x equals -2. There's no break in the graph, that's why it's continuous, but it is not differentiable because you can't take the derivative at a sharp turn. Number 2, state an x-coordinate at which f of x is positive but f prime is negative. Let's start with this part. F of x is positive. So that means we're talking about parts of the function that are above the x-axis. So we're talking about this, and this, and this. So we've narrowed it down to those parts of the graph so far. Hey, I should color coordinate this. F is greater than 0. Now f prime is negative. So this means that the slope is negative. Alright, so look at the green parts that we just highlighted and look for where the slope is negative. I think I'll just highlight that in yellow. This slope is negative. And I can see in this area the slope is going to be negative, and that's about it. So I can pick an x value in either of these yellow zones. I think I will pick this one right here and say x equals 1/2. Okay, so at x equals 1/2, f of x is greater than 0 because it would be about here, that's above the x-axis. But f prime is negative. The slope of the tangent line is downhill. For certain questions, you will need the information on this chart showing the graphical relationship between f, f prime, and f double prime. So memorize this chart. I would recommend that at the beginning of your next test or quiz, write this little chart in the margin so you can refer to it throughout the quiz. So, problem number 3, state an x-coordinate at which f double prime is negative, but f prime is positive. So remember, we're given the graph of f, so that's the key. If we want f double prime to be negative, f has to be concave down. Let's start with that. So where is the function concave down? So it's clearly concave down in this area, and it seems like it's concave down in this area. So that's a good place to start. Now we also want f prime to be positive. Well, let's see. If f prime is to be positive, then f must be increasing. So, what part of the area that we already highlighted is also increasing? So it seems to be increasing from here to here. And really all of this is increasing. So we could pick an x value from either of these yellow zones. For example, we could pick either -1/2, and for the directions you only needed one x value, but I'm going to pick one from each zone. So x equals -1/2 would do it, or x equals 2.5 would work. Number 4, state an x-coordinate at which f prime is decreasing. Let's just start with that part. So if f prime is to be decreasing, then f should be concave down. So where is f concave down? Well, I feel like we just talked about this. It's concave down here, and it's concave down here. Let's move on to the second part. The second part refers to function f itself. So we need f to be positive. Well, guess what? Both of the zones that we just highlighted also have positive f values because function f is above the x-axis here. So we can pick x values from either of these zones. For example, 0 would work. Okay, we could do 0, or we could do 2.5 again. So there's two examples. Number 5, circle the word in each row that best completes each sentence. At x equals 0, f of x is positive, negative, 0, undefined, or we can't tell. So we are being asked about f of x. This is a graph of f of x. So at x equals 0, which is right here, f of x is here. It is above the x-axis. That makes it positive. Okay, we are on this one now. At x equals 0, f prime is positive, negative, 0, undefined, or we can't tell. So we're talking about an x value of 0. F prime is the slope. So one way to answer this question is to understand that we have a horizontal tangent line right here. So the slope is 0. All right, we are on this one now. At x equals 0, f double prime is what? Well, we don't have an f double prime graph. We have an f graph. So we need to focus on that and make connections. If function f is concave up, then f double prime will be positive. If f is concave down, then f double prime will be negative. So let's check the concavity at x equals 0. So here's x equals 0, and this is concave down. Therefore, f double prime will be negative. We're on this one now. At x equals 2, f prime is what? Well, here is x equals 2 right here. F prime is the slope. So I see that we have a vertical tangent line here. So that means the slope is undefined, which means that f prime is undefined. This is number 6. Find the x-coordinates at which the graph of y equals 2x cubed plus 3x squared has a horizontal tangent line. A horizontal tangent line means that the slope is equal to 0. If the slope equals 0, that means that the derivative, y prime, is equal to 0. So we need to find the derivative and then set it equal to 0. Finding the derivative is easy. We will use the power rule. 3 times 2 is 6. Reduce this by 1. Power rule again. 2 times 3 is 6. Reduce this by 1. There's your derivative. So now we're going to set this equal to 0. So we get 6x squared plus 6x is equal to 0. Let's factor this. Actually, I feel like dividing everything by 6 because that's allowed. So that will give us x squared plus x is equal to 0. Now I would like to factor out the GCF of x. So I get this. And using the zero product property, I will set each of these factors equal to 0. And I come up with x equals 0 and x equals negative 1. So these are the two x-coordinates at which the graph shown here has a horizontal tangent line. Number 7, the graph of function f has been provided below. On the same axes, sketch a graph of the derivative f prime. No work needs to be shown. So on these problems, where you're given either the original function and you're trying to graph the derivative, or if it's the other way around and you're given the derivative and you're trying to graph the original function. Either way, the first step is to divide the function into intervals of increasing and decreasing. So in this first interval, function f is going downhill from left to right. So I'm going to highlight at the top here in blue to show that this is a decreasing interval. And then I see another decreasing interval right here. And that's it. I'm going to highlight my increasing intervals in yellow. So I see that it's rising in this interval and it's rising from left to right in this interval. Remember, we were given the graph of function f. So if f is increasing, then f prime will be positive. If f is decreasing, f prime will be negative. So f prime will be negative in the blue intervals and positive in the yellow intervals. One more thing. F prime represents the slope of this graph. So it would be helpful to know where the slope is 0. Look for those horizontal tangent lines, and I see one here and I see another one here. That means the slope at these x values will be 0. Therefore, f prime will be 0 here and 0 here. So in a minute, when we make the graph of f prime, it's got to pass through these 2 points. I'm ready to start sketching my graph of f prime now. Remember that f prime is the slope of this curve at every point. However, because in this first interval, function f is linear, that means there is a constant slope. We should be able to use the numbers and figure out exactly what the slope is for this segment. So it seems to be dropping down. It's a little bit more than down 2 over 1. So it's approximately down 2.5 over 1. In other words, the slope in this interval is approximately negative 2.5. That's a constant slope of negative 2.5. So for that reason, we should draw a horizontal line at negative 2.5 to represent f prime. So something about like this would be a good representation of f prime in this interval. F prime is the slope. The slope is 2.5 the entire way inside this interval. Listen to this important detail that students often overlook. Notice that we have a sharp turn on the original function f. You cannot take the derivative at a sharp turn. Function f is not differentiable at x equals negative 3. So that means 2 things. We should be expecting a discontinuity in the graph of f prime right here. There's going to be a jump here. But the other thing is f prime is not defined right at this point. So we really should put an open circle here to show that f prime is not defined here. So put a visible open circle here. So now let's pick up with the next interval. We have already decided that f prime should be positive in this interval. So I'm going to start drawing above the x-axis. And I'm going to have to hit this point. So I'm going to start drawing above the x-axis, but I'm going downward. I have to pass through that point. Okay, notice that I'm into the negative area now, but I'm supposed to be negative with my f prime, so this is good. So I'm negative, that's great, that's fine. But eventually I have to bend back and hit this point again. So I do hit that point, and as I naturally sort of follow through here, I'm into the positive area as I should be. So I can just continue this on, and that's it. Except for I should put another open circle here because, again, f prime is undefined right at -3. So this would be a decent sketch of f prime. For number 8, we're going the other way. The graph of a function's derivative, g prime, has been provided below. On the same axes, sketch a graph of the original function g. No work needs to be shown. So I mentioned briefly during the last problem that regardless of which direction you're going, your first step is to divide the graph into intervals of increasing and decreasing. So the blue intervals are where g prime is decreasing, and the yellow intervals are where g prime is increasing. Yeah, this graph is the same picture as before, but this time we are to interpret this as g prime instead of the original function. So here's where things change. Remember that we're given g prime, so we need to focus on the middle column. So we've highlighted what is increasing and decreasing, but now we're working backwards. So if f prime, well, if g prime is increasing, that means the original function should be concave up. If g prime is decreasing, then g should be concave down. So the original function g should be concave down in this interval, concave up in this interval, concave down in this interval, and concave up in this interval. But here's where we see that going from the derivative back to the original function takes an extra step. We've already divided g prime into intervals of increasing and decreasing. But now we're going to redo the intervals and divide g prime in terms of positive and negative intervals. So look at where g prime crosses the x-axis. That's where it goes from positive to negative. So in this first interval, g prime is above the x-axis, so it's going to be positive in this interval. And then it's below the x-axis, so g prime is negative in this interval. All right, this is a step that we did not have to do when we were going from the original function to the derivative. You only have to do this when you're starting with the derivative. Anyway, for the rest of this entire graph, g prime is greater than or equal to 0. It doesn't cross the x-axis anymore. So the rest of this is going to be one long positive interval. Technically it's 0 at 3, but we'll deal with that in another way. As far as these intervals go, we only have 3 intervals. So how will I label these in terms of what's going on for the original function g? So remember, if g prime is positive, then g will be increasing. If g prime is negative, g will be decreasing. So I'm going to label those intervals as increasing or decreasing for the original function. So the original function g should be increasing in the first interval, decreasing in the second, and then increasing for the rest of the way. So one more thing. Remember that g prime represents the slope of function g. So wherever g prime is 0, that means the slope of g is 0. That means we will have a horizontal tangent line here and here and here on the original function g. All right, again, g prime is 0. That means the slope is 0 in all of these places. You will have a 0 slope when there is a horizontal tangent line. So I think we are ready to start graphing the original function g. We're going to do it one interval at a time. So I'm going to erase some of these extra lines. As we go along, I will create a new interval anywhere there is a change. Either if it's a change from concave down to concave up, boom, I'll start a new interval. Or if there's a change from decreasing to increasing, or from increasing to decreasing. Boom. Either way, if there's any type of a change, that's a new interval. So for this first interval, function g should be increasing, it should be concave down, and it should end at a horizontal tangent line. Okay? So here we go. It's increasing, concave down, and it's going to end at a horizontal tangent line. My next interval is very narrow, but function g should be decreasing and concave down. And there's no purple mark here, so it does not need to end in a horizontal tangent line. It'll just be decreasing and concave down. So here we go. Concave down, decreasing. For my next interval, the function g will be decreasing and concave up. So picking up where I left off, and it should end at a horizontal tangent line. See the purple mark? So decreasing, concave up, and ending at a horizontal tangent line. So here I go. Decreasing, concave up, and ending at a horizontal tangent line. For the next interval, function g should be increasing, concave up, and it does not end at a horizontal tangent line. So here I go. Increasing, concave up, no need for a horizontal tangent line. Next interval, function g is increasing, concave down, and it should end at a horizontal tangent line. So here I go. I'm increasing, but I'm concave down, and the graph should end at a horizontal tangent line. In this last interval, function g should be increasing and concave up, and that's it. So here I go, increasing and concave up. So there you have it. This is a reasonable sketch of the original function g. That's enough for one video. I'll do the rest of this practice quiz on the next video.